Hi there, everyone. Another episode of some suggestions or hints to help you through webassign problems. This is from the third problem set, which is mostly about springs and potential energy graphs. And I think we did numbers 1, 2, 3 already, so this one we're going to start with number 4. And I think this is probably the hardest one out of the set, so I'll maybe do this one a little bit more slowly, and we'll see how it goes. It says we've got a block, it's released, we've got a mass here, I just put an M in there. And they say that it goes down and it compresses the spring a certain amount, and then it stops after that certain amount. So first thing we probably want to do is, they tell us, at least in my problem, says a spring that can be compressed by 2 centimeters by a force of 270 newtons. I think everybody have those same numbers, so we can definitely use 270. We can maybe change this into meters so that we get a spring constant, a K. So that's definitely another piece of the puzzle or a tool that we can use to continue on with the rest. Now letter A says, as it slides down and compresses the spring here, how far has the block moved down the incline? So we're kind of asking about that whole distance there in red. Well, we know that the energy from the spring getting squished comes from the block going down the hill. So that kx squared has to come from potential energy. We're just saying that all the potential energy in the spring came from the fact that the block started up high and all that potential turned into the stored energy in the spring. So we just found the K, we've got an M, we've got a G, and I think we've also got an X too. So we can basically get a height. Now that is indeed a height, which means that blue arrow there. That is not the answer for letter A, because if we got this height, we want to get this direction. We've got 30 degrees in there, so we want to do a right triangle. Let's just call this D, where we use a trig function. I'll let you decide which one to use so that we can get this side. It's just a plain old right triangle problem. That's letter A. Letter B is a little bit more tricky because it says, what's the speed of the block just as it touches the spring? That does not mean when it comes to a stop, because if it comes to a stop, that's just 0. They mean like somewhere up in here, somewhere as it's going along, sliding down the hill, right before it touches the spring. And the hard part is, we don't off the bat know where that is, because we have found this distance here, but that's not the distance when it first touches the spring. So I'm going to draw one more triangle. I'm going to call this D, this whole thing. However, this distance here I'm going to call delta X. That's the distance that the spring gets squished. So this would be like when the spring is not squished and then it gets squished a certain amount. So if we want to find just this portion in here, just how much it's going down the hill before it hits the spring, we can do the distance that we took and subtract from that our spring squish. Spring squish is not a physics term or anything, I'm just using that myself. So anyway, once we do indeed get that number for the triangle here, marker's kind of dying a bit, we will have this hypotenuse of the triangle. It's still a 30-degree angle, and so we can get this new H. We're just working with this triangle with a new diagonal distance here, and we're going to get this new H. Because it doesn't go all the way down before it hits the spring, it goes down less. With this new H, we can kind of do what we did here backwards. And what do we want to speed? Yeah. So we can kind of do mg new H mv squared over 2 and solve that for v. So this one is definitely a little bit tricky. It's not just a matter of blindly plugging numbers into some equation and getting an answer. Okay. So that's number 4. Let's do at least one more. I don't think I'll be able to fit all these into this video. I'll have to have another one. But number 5 is a tricky one too. They're saying that you've got like a tabletop where there's some sort of a spring firing gun and it launches something along the ground. They give you particular numbers for how much the spring gets compressed and basically like how far the thing goes. This is not only a spring problem, but this is also a projectile problem. Because the one thing we know, whether we shoot this thing fast or slow, actually it'd be like fast or slow, is that the time that it takes to fall is the same. So the horizontal distance the thing goes has to do with the time, which is the same, times a speed. Okay, so let me take a very sort of abstract, not a very concrete approach to doing this one. When we compress this spring and it shoots the thing out, we're saying that spring potential energy gets turned into kinetic energy. So we've got a k x squared over 2 and an m a squared over 2. Now, we're not changing the spring constant at all. That's a constant, so let me forget about it. We're not changing the mass of the object at all. Let me forget about that. We're not changing the number 2 at all. So really what we have is the distance we squish the spring is proportional to, that's what the little fishy means, the speed squared. And since both of those are squared, that means that the distance we squish the spring is proportional to the speed squared. Now, what does all this have to do with the problem? Well, this means that if you were to say double the amount of squish on the spring, you would double your speed. And because you're to double your speed and the time's the same, that means you would double your distance. So that means the amount of that we squish the spring is linearly related, or there's a linear relationship between that and how far we go. So that's a real more abstract explanation as opposed to just plugging into this particular equation. Let's see what you can do with that. And don't forget, I'm always happy to help you out if you need more explanation. One more. Number 6 again has a block that's moving, something that's going to squish a spring or compress it, I think. So what you probably want to get for letter A is just how much energy the thing has. Well, this block is moving, so that means specifically kinetic energy. And I'm looking at what we've got. Okay, we don't have a speed, so maybe we don't even want to get kinetic energy. Maybe we want to get the energy that's stored in the spring from it being compressed. So we can indeed definitely get that from the stuff that we've got with 1/2 kx squared. If we've got that amount of energy that is going to be stored in the spring as it gets squished, well, that means in somewhere here it says, where is it here? The coefficient of kinetic friction between the block and the floor is given. So that means we've also got some friction going on, some work being done by friction. So, yeah. And I think this is just good enough for letter A. So for B, for work done by friction, work done by anything is FD, and specifically it's F dot D. But we've got the friction going one way, and we've got the block moving the other way. It's kind of like a 180-degree angle. And so even though we might do the dot product with the cosine of 180 and get negative, I believe we're just looking for like a sort of an absolute value kind of thing. So we do indeed want to do F, which is the force from friction and the distance it goes. The force from friction is mu times the normal force, which is mu times the weight of the block times the distance. And I think with all that stuff, we should be able to get an actual number for the work done by friction. Okay, so I will stop there, and I'll do one more video for the last couple of problems.